So in this video, you're going to get the answers to the questions on your notes. So you already have a handout that matches what you're going to see in this video. So a vocab word, which is Avogadro's hypothesis. So what is it? So it's equal volumes of a gas at the same temperature, pressure, and that's going to contain equal numbers of molecules. So remember, same temperature and pressure, or standard temperature and pressure, is going to be the same as STP. So what evidence do we have to support Avogadro's hypothesis? Well, there's a scientist named Gay Lustig. His gas law and experiment noted that gases appear to react in simple integer ratios. So as a result, it was concluded that equal volumes of a gas at the same temperature contains the same or equivalent amount of particles. So why do scientists or chemists in particular find it so useful? And that's because the mass of various gases can be compared, and this provides the relative mass of substances. So what is relative mass? So in this problem you have, if the mass of A is 5 grams and the mass of B is 80 grams, what are their relative masses? So the mass of the lightest element is used for the mass ratios, and that's going to be the case in every problem that you do. This will allow the masses for other elements to be assigned. So if you look A versus B, which has the lightest mass? That's going to be A. So if you look here, there's a 5 gram divided by 5 gram setup, because remember, 5 is the lightest amount of the elements. So that's going to give you 1 gram of relative mass of A. And then you do the same thing with B, but it's also going to be set up to 5 grams. So 80 grams of B divided by 5 grams of A is going to be equivalent to 16 grams, which is the relative mass of B. And later in the other video, you'll find out this is the same setup that you'll use for empirical formula and molecular formula. So what is molar mass and why do chemists use it? So molar mass is how much mass to how many atoms. How much mass to how many moles. So you can determine the molecular formula of a compound from the molar mass. This will also allow you to determine the percent composition of elements in compounds once you have the empirical formula. So remember, once again, you're going to learn to calculate the empirical formula later, but you already know a vital step, which is determining the molar mass. So how do you find the molar mass of a compound? So that's going to be on my next page. So here's our problem. The molecular mass is calculated by taking the mass of each element. That's step 1, the mass of each element, and then multiply each individual mass by the amount of atoms in each element present. That's step 2. Step 3, you're going to add each of the individual sums together. So here you have H2O1, which is the same thing as H2O, which hopefully by now we all know is water. So first thing we're going to do is calculate the mass of each element. So the mass of hydrogen is 1 gram. You have 2 hydrogens, so you'll multiply by 2. So 1 times 2 is 2 grams of hydrogen. Then you have oxygen, 1 atom of it. 16 times 1 is 16 grams of oxygen. And then our final step, we add those terms together, or those amounts together. So 2 grams plus 16 grams gives you a total of 18 grams. So not hard at all, simple math. So then our next goal is to convert the mass of grams, which is G, to moles. So this is where your roadmap would come back in handy. So you're going to set up the conversion by, remember, you're given, that's going to be multiplied by your desired unit, which is 1 mole of compound divided by the molar mass of the grams. So this is where you would pull out your roadmap. So mass 2 grams. So once again, you look at your roadmap and you want your answer in moles. Moles is the center. And then you started out with the molar mass. So you're going to use this conversion factor, your given multiplied by 1 mole divided by the molar mass. So remember, your like units are going to cancel, then you're going to multiply across and divide by the denominator. So we're now talking about 5 grams of water. So 5 grams is our given. 1 mole is going to be at top of your numerator. And then 18 grams, because we previously calculated that the molar mass of water was 18 grams. So 5 multiplied by 1 is 5, and then you're going to divide by 18. So then we will get this simplified formula right here, 5 divided by 18, which is going to give us 0.28 moles of water. So you just did a one-step conversion for calculating the conversion of molar mass to mole for water. Now, how many particles are in a mole? So go back to our roadmap. So how many particles are in a mole? This is our representative particles. We want to know how many is in a mole here. So 1 mole is going to be at the top, and then 6.02 times 10 to the 23rd particles at the bottom. So how many particles are in a mole? Remember, 1 mole is always equivalent to Avogadro's number, which is 6.02 times 10 to the 23rd. So if it's element, atoms, molecules, which is your covalent compound products, or your formula units, ionic compound products. So next, so we want to see some examples of calculating the number of molecules or atoms in a sample compound. So remember, molecules, atoms, formula units are all the same as your representative particles. So our problem, it says, an old pre-1987 penny is nearly pure copper, and you know that the unit for copper is Cu. It says, if such penny has a mass of 3.3 grams, that's going to be our given, how many moles, which is the unit MOL, of copper atoms would be in 1 penny? So it gives you everything that you need. It tells you that you have the mass, or you're given, of 3.3. You're trying to determine how many moles, so that's going to be our numerator. And then of atoms would be in 1 penny. So you're going from mass to mole. So here to here. So 1 mole is going to be at the top, molar mass at the bottom. So first we need to remember, what is the mass or the molar mass of a copper atom? And if you check your periodic table, you'll see it's 63.5. And remember, that's the bottom number, your mass number at the bottom. Then we're going to remember our setup. Your given multiplied by desired unit divided by your canceling unit. The canceling unit and the given unit will be crossed out. So then we have 3.3 grams of copper multiplied by 1 mole of copper divided by 63.5 grams of copper. So you multiply across and divide. 3.3 times 1 is 3.3. And you divide that by 63.5, and you'll get 0.052 moles of copper. So then you'll notice that 8 acts about percent composition, 9 empirical formula, and 10 acts about molecular formula. That'll be determined in another video, so please hold on to your notes for this unit. Thank you. Keep practicing.